So, thank you to Dotan for the presentation about the overall, the journey. So you saw a big part of it is basically the open time server. So next we have the open time server, basically more in details by Julian from Meta and Alad from NVIDIA. So with no further ado, guys, the floor is yours.
Am I on? All right. So hi, hello again. Open time servers. This is the first work stream that we announced at TAP, and it goes to the top of the tree, to the very first element that we want to focus on in this session, which is the time server, Grandmaster, PTP Grandmaster, or however people refer to it. That was one of the first things we had to look at when we try to design a modern, scalable data center which is time synchronized. So we're going to go quickly through the reference architecture, and we will discuss how they are built with time cards and what are time cards. My friend Julian designed those, and we'll give you the information on that. We'll talk performance. We'll talk what's going to be up, how can you acquire such a server, and where it's available. So let's go right in. And as for orientation, the first element, of course, is the top of the tree or the bush, the PTP bush that we're designing here, and that would be the source of the time in the data center. That's the first element. And when we went to review what are our options, so where do we start? Who are the players in this market? What are the features they are having? And if we can adjust those to fit into a modern type of hyperscale data center requirements when it comes to the way that it is managed, the way that the scale, the eventual scale that we want to reach to that. When we found a market which is addressed by multiple players, and it seems like each of them have a portion of the market, but none of them have a strong dominance, and that's good. It signs that the market is active. And we also noticed that the feature set or the differentiations between them come from proprietary software, proprietary features, which are hard then for an operator, say like Facebook, to go and utilize that in a way which is which transcends beyond vendors, or in a way that they can use that at scale with some vendor agnostic approach. And so that was one of the first realizations we noticed. And the other thing we have seen is that when we were trying to ask for elaborations or modifications, or to buy, say, 100 gig capable type of Grandmaster server, these things were not easy to negotiate, and were not available at the time that we were asking. Another thing we noticed is that there was a lot of licensing around it. So a lot of the features I was talking about, they are licensed, and they are coming from the vendor who has worked hard on that. But if we want to try something, then you have to work these licenses fees. And also, it may slow down your innovation if you want to code on top of that. And the approach we have taken is probably a slide you've seen elsewhere with OCP. The approach we're taking was to disaggregate the hardware from the software and open up, to the best we can, the references of the hardware and the stacks, the APIs, or at least the guts of the software. So we will be able to install it, and we'll be able to install it at scale, modify that, and also to bring our own innovation in a way that we can work as a community and invest into this product and come up with a richer, thriving ecosystem, which we can now help build as a best-of-breed product and bring it to the right market fit that we need. And what we're having here is essentially 3 layers. The first fundamental layer is the fact that you can take any server that you want and use it as the basis of the Grandmaster. It allows you to pick your server vendor, and you can have your trusted one there. And of course, it has to meet certain specifications. They are met in the spec, and we'll go into them. But the next element is that you bring a time card, a time source. And we have specified that in a way that the time card is defining characteristics of what are the holdover, what are the accuracy figures they want, but it doesn't tell you how to do that. That would be the time card specification we'll see forward. And then, of course, you need a NIC to dissipate time. And lastly is the software. It's the engine that runs the server, ability to go and extend it to the million of clients that we wanted, and also manage it, achieve telemetry, achieve the control of it, achieve debuggability over it. So you have all the tools above it, which are part of our open source community, and we're adding to it. If you look a year ago, we were not on stage, it was a virtual stage, but we were talking about the Grandmaster, the open server, and it was still a lot of screws and wires. That's the work of Facebook here that we're documenting, and a napkin sketch that turned into a hack, that turned into a lot of bolts and wires coming out of servers. But eventually what you have is on the right is one of the first prototypes, and now we're going to show you basically that we have the reference architecture up, contributed on our tap. It's the first contribution. It's the first work stream that sees the light, and it has these 3 layers. One other thing I would note is that these building blocks, whether you take a time card or a NIC, or some vendors, as you see here on the right of the screen, have a time and NIC combo PCI card. These can be bought in the free market and can be swapped as you need them, as you go with speeds or as you go with your different flavors. And they're all available as OCP-inspired products on the marketplace, and if they're not there, they will hit there in a matter of days, since the specification is now open, and we have a few sources of time cards and a few sources of NIC time cards for the selection. And of course, you know everything about servers. With that, I will hand it over to Julian.
Hi, so to look inside the time card itself, as Elad described, we have to talk about what is different from a traditional closed source Grandmaster versus an open time server. So in this diagram, you can see what's actually separated out into the time card versus what's in the NIC. So in order to get the time onto the device, we needed the PCIe bridge to have it act like a normal PCIe capable POSIX clock, same like any commercial NIC that acts as an ordinary clock. But then on top of that, we also needed to have the GPS time in order to get globally accurate time, the time of day, and the PPS. So to do that, we have a GNSS receiver on the board, and then we also have a high stability oscillator that's disciplined by the PCIe bridge, the FPGA PCIe bridge. So between the two of those, you're able to get highly accurate time anywhere in the world with the open time server, and you're also able to have extremely long holdover. So one of the issues that we were having at Meta was that if you have maintenance windows in the data center, you need to have high stability for that maintenance window. So if the technician is in a 24-hour SLA, you need to be able to maintain accurate time within your error bounds for that entire SLA. So for our design, we were looking for a high stability oscillator capable of holding greater than 1 microsecond holdover accuracy for 24 hours. So these are some of the performance tests that we've done with our current reference architecture. These are both measured with the CalNex Sentinel. So the graph on the left and the right are the same test, but over different timescales. So when we were talking about 1 microsecond over 24 hours, we also need to know what are the limits that we're getting at with our current oscillator. Are we getting 0.9999 microseconds in 24 hours, or are we getting 100 nanoseconds in 24 hours? So these tests were done on our reference architecture, the same as described, using a commercial off-the-shelf HPE server with the time card with the SA53 and a normal Mellanox CX6 NIC, which is commercially available. So nothing closed source, nothing special, nothing magical. And the test that I ran was running a temperature cycling during holdover. So the worst case is you have extreme temperature cycling of the oscillator while it's in holdover, after it's been disciplined for approximately 24 hours and then goes into holdover. So more extreme tests would be like 10-hour synchronization and then holdover, but that seems a little unreasonable, so I went with 24 hours. So as you can see from the graphs here, the left axis is the time interval error. So actually, the scale that it's on, over 3 days, it didn't go below 500 nanoseconds. So that gave good confidence that our current reference architecture and current oscillator design is able to give us the 1 microsecond over 24 hours at normal data center operation. Because obviously in a normal data center, we're not going to be cycling 15 degrees up and down every 2 hours. So these kind of tests gave us high confidence that the reference architecture that we have is solid and will be able to meet our performance characteristics needed for our data center deployment. The right side is the same test. So the automation was running the temperature cycling and then stopped. So that was over 5 days, and it didn't go below, it never crossed 1 microsecond. So even though we only synchronized the atomic clock and the FPGA for 24 hours, we were able to maintain holdover less than 1 microsecond for that entire 5-day duration, even after temperature cycling. And even as the graph shows, the temperature cycling itself doesn't have as much impact on the oscillator performance. Even after it stops temperature cycling, it's still following the same characteristic curve. So these kind of tests are what we've been working on in Meta. We've been trying to characterize the hardware performance, the software performance. As has been mentioned, we've characterized up to 1 million clients for the software side, and then for the hardware side, we're measuring the time card performance in order to make sure that the hardware is up to spec for what we need in the data center. Some other features that we've been adding into the time card. So there are a lot of neat features that the time card can give you. So the most important ones are the PPS input and output. So for traditional appliances, you might have 1 or 2 PPS outputs, 1 or 2 PPS inputs, which can be used to timestamp external events. So for future revisions of the time card, we'll have the 4 SMA connectors on the front panel that can be, any one of them can be configured as an output or an input and can be used to either send PPS output for accurate timing distribution, or it can be used to externally timestamp external events into the time card to give you highly accurate measurements up to 4 channels on a single time card. So for this application, it might not need such a high stability oscillator. It depends on the customer use case. So also we'll be having other revisions of the time card with different oscillators available. So different customers can use the time card for their need. If you don't need the high stability over 24 hours or multiple days, you can use a lower end oscillator, and then you can still have access to all these features such as time distribution, time stamping, and general time server applications. So the hardware side is what I've been working on also, but I've also been working on the software side, and a lot of engineers inside Meta have been working on the software side. So the PTP4U is the main glory software part of the time server. So that's what is the actual Meta implementation for a scalable grandmaster. So instead of an FPGA implementation that gives you, say, 1,000 clients, this is a Go code that runs over 1 million clients on a single socket off-the-shelf server. So with this code, as it's been contributed to GitHub that anybody can contribute to, you can raise requests, you can ask for help. So this contribution allows anybody to deploy, even on a small server. If you have just a normal server with a 1 gig NIC and you don't need globally accurate time, you can still run this to provide synchronized time to multiple machines. If you add a time card even to like a home PC, you could run PTP4U on that and distribute PTP anywhere that you need it. So with this software, we have reliability, and there's a lot of telemetry built inside. So even if you're running 1 million clients, you still need to see how many packets per second, how many clients are connected at any given time. It's all exposed through documentation and telemetry calls on the PTP4U. You can access that from anywhere that you need to monitor the PTP Grandmaster. The other end of it was the testing side. So in addition to commercial applications such as Keysight or Spirent or Calnex, there's also, if you just need to load it up, you just want to see, is your server going to crash? Can it handle how many clients? We also developed Client Gen, which is a simple Go-based traffic generator that can do also millions of clients and can give you latency and telemetry tracking for each client. So this allows us to, using also any commercial off-the-shelf device, you don't even need a time card. It can just simulate clients, and then if you wanted to measure the performance of your Grandmaster, you could hook up a commercially available measurement equipment such as Calnex or any other device, and you can see what the Grandmaster does under load. So there are lots of options for the Grandmaster. You can deploy small scale, you can deploy large scale, time card, no time card. For traffic or testing, there's client gen. You can also use a time card to test another time card. So if you have a time card that you keep synced to GPS and you want to test another one, you can take the second one off GPS. You could timestamp one that's synced to GPS with one that's not synced to GPS. So even with the time card itself, it can almost act as a measurement device of another PTP device by itself. So that's something that we've been using a lot. As a reference point, here's where we've shown all the different progressions of time cards. So on the left is a measurement of the time card itself on the CalNext Sentinel, as we mentioned. You can see that even though it's got spikes, the overall time error that you're getting out of the time card is less than 50 nanoseconds or better. And
Impressive.
Hmm?
Impressive.
Yeah. So this is a normal operation with the GPS synced. So even though you're bouncing around a little bit, you still have that high precision on the time card. And then that's easily accessible to the software, to the PTP4U, to any device that needs to get it distributed to them. The other examples here are shown the ecosystem of time cards is now evolving. So we have the Meta time card, which started as the napkin sketch in the top left. We have Aurolia's time card, which is similar to ours, but using their oscillator and their FPGA implementation, which gives very similar performance to the Meta design. The Meta design, currently we have a few different versions. So we have to support different oscillators, the cesium clock, rubidium clock. We have the SA53, the Symmetricom, the CSAC. We're also working on a few other revisions to support OCXO and other oscillators that are not quite as high-end as atomic clocks. There's the NVIDIA design, which has the GPS built into the CX6, which can give you accurate time at the NIC, and you don't need an additional card in your server. So if you're running a small server and you don't want to burn PCIe slots for a time card by itself, there's NIC options that have it built in. The same with the Intel design there, where they have the GPS and the OCXO built onto the NIC. So that way you can have one card that gives you the time card and the NIC in a single device that runs with normal drivers that come from Intel, come from NVIDIA, and then it'll just act like a time card, and you don't need anything else. We're good on time?
Are we good on time? I think we are.
So the call to action that we have is all the hardware design, all the software design so far is all on the GitHub, opentimeserver.com. We'd like any participation, mechanical review, electrical review, suggestions for future development, suggestions for software development. Anything that you want to contribute would be greatly appreciated. We're all open to any suggestions and any interesting use cases. We love to hear interesting applications for time card beyond PTP Grandmaster. If there's any kind of measurements that people want to run using the time card or using the time NICs, that's always great to hear about different uses that we didn't even think of and that we could help develop with software or any kind of engineering support. We have articles about what we're deploying, how we're deploying it, our timelines, and what our future plans are. So any kind of contribution from any open source community would be greatly appreciated, and we're always open to any suggestions or work from anyone else.
I would extend the call to action to servers, system vendors who would like to productize an open time server as a whole. This will be the reference architecture, and we'd love to hear from OEM servers, several ODMs who are wanting to partner with us and get the OCP-inspired time servers. And with that, open up the floor for questions.
One more thing. Yeah. So one more thing I want to add is we have now a work stream led by Anand. But what was it, Anand? Instrumentation and testing. So for example, the client gen or like other efforts, let's say with a time card, like acting as like a testing device and all these things, they will go basically under that work stream, and we're looking for even more derivatives, let's say, from the time card that can be used just for testing. And if you go on the ocptap.com, It leads you basically to the link to the wiki. You can go on the wiki, you can see this last work streams that we have right now up. Okay, so let's go for questions. Yes. Sure.
Okay, thank you very much for sharing the experience. Just my curiosity, what's the most difficult part of this application you experienced, and then the most challenging part, and how we can work together to achieve and to move this forward? Thank you.
I will repeat the question. What was the most difficult part of this design challenge, of this design spree, and how can we work together on this challenge? I'll give my view share with you. So in my view, the biggest part was to believe that we can do that. The moment we said, hey, this is a grandmaster, let's open the box and look what's inside. And if we carefully look at what we need to work, what we need to own in order to reach the serviceability and the operation that we need, that was the hardest part. After we jumped in, it was with the right mindset, we were able to get there pretty quickly. So in less than a year, we are up and running. But honestly, he did all the hard work. So.
Okay, Julian, let's add a little bit the technical challenges.
Yeah, so I'd agree with Alad's point there. So if you have a commercial off-the-shelf Grandmaster, basically it's not your problem, it's their problem. But once you put it into an open time server, you own the hardware, you own the NIC, you own the software. Any kind of deployment issues such as needing the 24-hour holdover is a big requirement. So that's a pretty unique requirement from other Grandmasters. We have to make sure the hardware is up to spec. We have to make sure we're using a good oscillator that we can source, that is reliable and meets all of our requirements. Those kind of challenges were things that is different than an off-the-shelf server or off-the-shelf commercial Grandmaster. So if you don't have a Grandmaster from a company that supports 24 hours, there's not much you can do. I mean, you can ask them, but once you take it all into your own hands, you have to be able to list out all the requirements, but also meet them. So the other challenges were like on the software side for the server implementation, the Linux PTP stack wasn't really designed to scale to 1 million clients. So like the PTP4L client that was built into Linux is designed for basically one server, and it can provide clocks to, say, a couple hundred other clocks. But if you want to scale that to 1 million, all of a sudden you have to really dig down into the Linux and see how is it getting those timestamps, particularly from the transmit side. So when you're sending out packets to an ordinary clock, you need to also get the timestamp that the NIC sent that. Those kind of driver implementations weren't really optimized for large throughput, high client count PTP traffic generation. So those kind of issues that we ran into where it was fine for Linux, 100 clients, 200 clients, it's okay. But as soon as you try to scale to 1 million with a single NIC and a single server, then we really had to dig through how is the driver implemented, how is the NIC doing the timestamping, how is the software handling that, how does the software scale? So you don't want to send one packet and then wait for that packet to get sent. You want to do some scheduling, you want to do some threading, multi-threading. So all those kind of issues that we had were things that had to be taken care of before we could say that the OpenTime server was operational, because if we just ran the normal Linux implementation, then it would have been dead like within the first week, because we needed obviously more than, once we lost the boundary clock, we had to scale way beyond anything that was out there. So it was all kind of open water. We had to see what the issues were. Is it the hardware issue? Is it the software issue? How do we improve what we find? And that was a lot of work from internal team, software team, production team, hardware team, thermal team, mechanical. Everybody was involved in solving all these kind of issues internally.
Yeah, adding to Alad's comment about, like, again, the mindset and like basically thinking everything is possible, and also to what Julian said, like about the technical things. One thing that sticks out for me is those errors that they show up spontaneously, and you have a hard time, let's say, in terms of like replicating them and explaining them, and then you finding a root cause. They were, let's say, the most challenging one. And because you're operating at, let's say, at a region that the test tools are also like not spec'd for that, you know, like let's say test tool tells you, like, let's say you're around, let's say 20 nanoseconds. And then you're pushing the test tool to check like how is this like cutting edge rubidium clock performing, let's say, single digit nanoseconds. And then you get like a spike out of nowhere, and then you can blame anything in the system, like from software to hardware to thermal to, this is where it becomes a challenge. Like basically, devil is in details. I will say like the details were always challenging. I don't say all of them are solved, but to a large extent, most of them are taken care of that we are, let's say, ready to deploy.
Next question.
Yeah, just by the way, congratulations. So 1 million clients is amazing. Now, the question is...
Take your mask off.
Oh, yeah. The question is, I would assume the reason you want to scale up that far is you assume your own switch fabric has no boundary clock or transparent clock capability. Is that right?
Yes.
So, but what if all the new switches that can do the boundary clock, if that's the case, do you still need that scalability? That's the first question. And second is, what is your, on your normal Ethernet NIC card out of that Grandmaster server, what is your accuracy in terms of, are you looking at a class C or looking even close to a class D that is yet to be fully defined, or you're basically just class B and you don't care, class B is fine enough? Sure,
so 2 questions, thank you. I'll repeat the first one. We mentioned 1 million clients, and the question is it because we have, we have a switch limitation going into transparent clocks without boundary clocks? Dotan mentioned that as part of his session. Would you like to take the answer again?
I think that we said that the lack of boundary clock gave us an advantage that each node can measure his own error bound. So this disadvantage came into an advantage. But if you do have boundary clock, then of course you don't need that scale. You will need to figure out how you're going to measure your error bound.
So we have the error bound propagation and we have the scale. And we found out that with transparent clocks, we're solving one problem. In fact, we're solving the other as well. And that's kind of like the trick. And then the second question was, sorry.
One thing I want to add to the first question. So there is in IEEE 1580 version 2, the variance at scale, which is usually from the grandmaster, like disseminated down to the clients. With boundary clocks, it's still challenging. So again, elaborating on what Dotan mentioned, this was a disadvantage that we couldn't have boundary clocks, but at the same time, there were other issues that really got resolved with this disadvantage and all became advantage, such as that like you want to have like let's say one loop that you go through, so you have maximum transparency to one grandmaster, and then from there open time server, and then from there to UTC you have like some calculation that you know, okay, this is my variance to UTC, and now here is like the rest, and then from the servo's perspective, okay, this is my variance, and I add this to it, so I have the total variance, and then I present this, let's say, to the application as this is the total error bound. So let's say with the addition of boundary clocks, great, you bring them in, you probably will have less need for, let's say, scale, but you can always increase frequency if needed. So then you have more information about, like, let's say, how the network is performing and so on. Mm-hmm. But it's a capability. It's not like it's like grossly scaled up that it doesn't make sense now you're using a time card while you have only 1,000 clients. No, it's not a problem. Like, use it for something else.
Let's go to the next question. We're running out of time. Dotan, please.
Julian, thank you for inspiring talk. Again, this is an amazing thing. I want to ask, you said that the openness of the software gave you the responsibility feeling that you now need to solve any problem. I want to ask on the other side. I see the openness as an opportunity to now have all the knobs and understand what's happening and what can you correlate events in your data center to a time event. I will dare and ask, did you see any fruits out of that lately already or not?
Fruits of having time synchronization in your data center how is that helping
Debugging.
your debugs or your other activities within the data center. Would you like to answer that?
So that's one of the things that we've been looking at. So one of the issues that if you've ever debugged at a data center scale is you start looking at logs and nothing correlates. So you look at one machine, it has one time. You look at another machine, it's like 5 seconds off, but the event happened in the millisecond range. So these kind of time synchronizations have provided, even in the short term, in the devices that we've been testing, the ability to debug at a very low level what happened in what order. So even jumping between different machines, different logs, you're able to see the actual order of events as opposed to kind of an arbitrary order of events.
A coherent timeline.
Right. So no matter which device you look at, you can see what's happening.
All right, we're going to take the last question and call it off since we are going for the next one. Go ahead.
Just briefly, there was discussion of the transparent clocks, but we haven't heard much about how that was done, how it was implemented. Was it full on-path
You
support?
should stay with us. Stay with us for the transparent and boundary clock session. It's the last one for the day,
Standing by.
11:30.
So one more thing, like you asked about the second question. So you asked about the granularity, let's say, from the time card, and then when you go on the front end NIC, what will happen, right? Was that correct?
That's it.
Basically, just want to know the accuracy. For
Sure.
example, are you 8273.1 class B, class C, or
So
class D?
so with the
quick
time
answer.
card, you go on with the time card is class A, but then when you go on the NIC, it becomes class B, and it depends on like if you want to go, let's say, with a PCIe bus. If you want to stay with a PPS, you go like from the time card with a PPS, external PPS to the NIC, you can stay at the same class A. You go plus minus under plus minus
actually
5
going
nanoseconds.
from-
Guys, that's a wrap. Let's take the questions
Let's take
here.
it off.
We're going to be here all day and online with our other teammates who are supporting us online on the chat. So let's head it off to the next session. Thank you.
Thank you.